why is my neck broken. Whoa! Ah! Hello? YouTube studio, fix yourself? Okay. Hi. Hello. Yay! 聞こえますか？こんばんは。こんにちは。はじめまして。I'm Usagi. Yeah, we're going to be doing slop today. Woo! Woo! I know it's really late. I feel so bad. I'm so sorry. I swear I thought I timed it properly so that I would be able to like start streaming like in the afternoon, but then I'm stuck with the late hour schedule again. I feel so bad. Man. Gomen. But we're gonna be doing educational stuff, man. This is awesome. This is so freaking awesome. I've watched a couple of this person's lectures before and I think they're pretty good, so I'm a little bit excited. I might turn it on to 2 times speed though, because I've seen this and I just want like a refresher bit. So see. Let's turn the back speed to 2.
We're live. Welcome back, everyone. How are you? Very happy to see you again. Mostly because I'm finally done with my exams and we can go back to we can go back, huh?
Yay.
Nope, not till I graduate. So we can finally go back to our regular schedule of 6 to 9 p.m. lecture. This first day's gonna be tough for me because I just took a 3-hour exam this morning and then came here. It's gonna be hard. So excuse my lack of energy and maybe if I'm not as funny today as I usually am, give me a pass, right?
Is he cracking open an energy drink? That's crazy.
Exactly. That's actually very true. If I don't curse as much, you'll know something is very, very wrong. And something is very wrong today because I have to teach nomenclature and I fucking hate teaching nomenclature. Chapter 1. Nomenclature.
That's so real, bro.
And now the people in the room are like, what the hell? We just did chapter 3 and 4, why are we going back to chapter 1? We're revisiting chapter 1, because I didn't want to teach chapter 1 before, and now we have to circle back on. Can you guys see the red? Is it like too light? You guys can see it, right? Okay, good. Cool. I hate teaching nomenclature. I absolutely hate it. It is the worst. And I would rather not do it.
Really
so what I'm
is.
going to do is we're going to play Read the Room, and we're going to see if you guys are capable of naming the molecules I put on the board. And if you're not, then I need to waste my time teaching you how to do this. So it's on you. My mental health is in your hands. Ready? Right. I don't care if you're not ready. Neither am I. I want you to name this. I want you to name this.
Wait, should I try naming it?
And I want you to name this.
Wait, should I pause and try naming it? Hold on. Wait. Okay, the first one, it has 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5. Wait, 5 carbons. 5 carbons. Right? 5 carbons. Yeah, 1, 2, 3, 4, 5. Yeah, 5 carbons. It has an. I think that's a carbonyl group. It's a carbonyl group. And then it has a 1 methyl substituent. Then wouldn't it be? Because I want it to be on. The family group always has to be, so. I think that's a key. What do ketones get named with? Ill? No. Formaldehyde. I think it's IDE. So then it would be 4 methyl 4-methyl pentide? 4-methyl pentide? 4-methyl pentide for the first one. The second one is 1, 2, 3, 4, 5. Yeah. Or 1, 2, 3, 4, 5, 6. Oh. 6. 1, 2, 3, 4, 5, 6. Yeah, 6 carbon chain. Okay, 6 carbon chain, right? 1, 2, 3, 4, 5, 6. Carbon chain on the third carbon. Wait, that's kind of bad, Loki. What the fuck? Wait a minute. Cause I want. No matter what, I think the carboxylic acid has to be one of the highest. Well, how would I count? Okay. On 3, I have a carboxylic acid. 1, 2, 3, 4. On the 4, I have an. I think that is a terbutyl. Terbutyl. On 4. So it would be 4 terbutyl. 3 acid. Shoot, I don't remember the name of carboxylic acid. So acid. It's acid. Okay, let's go with that. Let's roll with it. If I get it wrong, oh my god, GG. GG, that is so bad. 1, 2, 3, 4. 4 carbons. 4 carbons is butane. First group we have an aldehyde. We have a carbonyl. Carbonyl. First one you also have chloride. Chloro and bromo. And the first carbon. This is on the first carbon. So on the first carbon. And then we have 1, 3, the third. Third, right? So it's 3 bromo. 1 chloro. butyl. Okay, wait, let's see if I got it right.
I will try to name them.
It's just oh my gosh, please let me get this
In my
right.
head. Thank you for wishing me good luck. I changed my mind.
What the hell? Why'd you change your mind, bro?
Actually,
You're so mean for that.
there we go.
What the fuck? No! Oh man. Wait, I
I'm
don't
not
know.
gonna say it on camera, but if you guys fuck this up. So, now my life is also in your hands. I'm kidding. That's a joke. Future Doctors of America, am I right? I called my buddy earlier today after the exam was over. And he's like, oh, yo, how'd it go? I was like, it was
Do we really need to know this for the MCAT? Yes! Yes, OTR! It's like one of the most important things. You literally can't freaking answer the questions unless you know like the chemical names. Like they won't outright give it to you. Sometimes what I heard they'll do is like they'll give you the um the structure. I don't really recall having to do much identification with taking this. No, it's because what was I saying? In the question, maybe they'll give you like the common name or something, and then like they'll expect you to try to like what is it? Find an answer based on the IUPAC name. So you would draw out a structure first, but then you have to be able to name the structure to be able to identify the like answers in the question.
fine, it's fine. He's like, oh, like, what do you do? I was like, I'm gonna bring coffee to teach. He's like, oh, you're not chilling with your friends? I was like, nah, they're all just gonna go drink. I'm like, I don't drink. I don't really party like that, etc., right? So he's just like, isn't that kind of ironic that all the people who are gonna be doctors finish their exam and just go drink? I was like, dog, I will tell you, I have never met a stupider bunch of people than me and my friends. I have never met someone with less collective IQ than me and my 4 roommates. All right, you guys ready to go over? Okay. What did you name this compound? Nothing. You didn't name the compound? Did you name the compound? Sarah, what did you name the compound? 4-methyl. That is correct. So we have a very high priority group right here. Like it's 1, 2, 3, 4, 5, or 5 going up. It doesn't really matter.
I feel like they're like this question web services will make you study. Oh well, I feel like it's good review for me though, because it's like you start from the basics. Like it seems good. It's good to know though. Just so you get. Maybe I should try naming this. Carboxylic aldehyde always wins. One, two, four. There's 1, 2, 3, 4, 5. There's 5 carbons. 5 carbons. Right? 5 carbons. And then since there's that's gonna change from butyl to pentyl, and then on I want the lowest carbon to have it. 1, 2, 3. It's gonna be 3. 2, 3. Four, 4 bromo. 1 chloral. 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 Pentyl. You definitely need to know the names of the functional groups and how to count carbons interchange in ring sugars. Are you being sarcastic? Don't make fun of me. I'm a chronic overthinker. I wouldn't know. I can't read. I can't read the room.
Matter because you can rotate about that
My
bond.
Kiyomi
Right?
is
So we have
not
4
coming
methyl,
through. 4 methyl.
2 pentanone, or you can
4 methyl 2 pentanone. What? Wait. Oh shit.
You can also say 4 methyl 2, or you can say 4 methyl pent and 2 one. Further designate.
God damn it, we already got it wrong. It's not 4 methyl pentide. The fuck is a pentanone? A pentanone? ONE is the ending for a ketone. The suffix dash 0NE or 0 ONE for ketone. Okay? Pent is for the fact that there's 5 carbons. And since the ketone is on carbon 2, or it starts on carbon 2, then you would do 2 pent. But then you have to add the suffix at the end because what is it? A ketone is the most makes the carbon number 2 the most oxidized. If I remember that correctly. But damn, God. Okay. Carbonyl. The ending is ONE. 4 methyl 2 and one and 2 4 methyl and 2 one. That's crazy. What the hell?
Designating that the ketone exists on the 2 position, right? And the reason we do that is because sometimes there's a double bond in the molecule, and we want to specify the double bond differently than the ketone, right? So that's one reason that we do that. Can someone run to any bathroom and grab me a little paper towel or something? Thank you. Drop it on the corner of the table if you don't want to be on camera. Okay, what's next? You have this very weird looking behemoth of a thing. When you're numbering molecules, you obviously go for the longest chain of continuous carbons, correct? But you also go for the longest chain of continuous carbons with the least, thank you, with the least number of substituents, right? So let's take a look at what I mean by that. So we can start here, obviously, because carboxylic acid is highest priority. We go 2, we can go 3, 4, we can go 3, 4, 5. We go 5, right? We go 3, 4, 5, or we go 3, 4, 5. But if we go 3, 4, 5 down, that's 1, 2, 3 substituents. If we go 3, 4, 5 left, that's 1, 2 substituents, right? Let's go this way. What is this group called? It's called an isopropyl group. Very good. Yeah.
God
So
damn, it's not terbutyl. I'm an idiot. There's not 6 carbons. Where the fuck did I get 6 carbons from? Oh, he started at the freaking carboxylic acid. Oh. Oh, hell no. Oh my god. Wait. 1, 2, 3, 4, 5, right? 5 carbons technically. Then not terbutyl, this is isopropyl. Oh my god. Jesus. One with the most substitute too. It's okay, I don't know what these are. We're gonna find out together. This is a learning experience. This has to be educational.
Iso, just know that it ends in a little V, right? So this would be thank you. This would be isopropyl. This would be what? Isobutyl, because it's 1, 2, 3, 4. This would be 1, 2, 3, 4, 5 isopentyl. Whenever it ends in that little V, it's iso.
Oh,
right?
iso. Iso is
Iso.
the V.
So that is an isopropyl group. What do we have on carbon 2?
Okay.
What do we have on carbon 2? Ethyl, yeah. And what do we have on carbon 1? Carboxylic acid, right? So what comes first? 3 isopropyl or 2 ethyl? 2 ethyl because it's first alphabetically, right? 2 ethyl 3 isopropyl. 1, 2, 3, 4, 5 is pentanoic acid.
Oic
AN, not
acid.
EN.
Okay. Oic acid.
Because there are no double bonds in here. If I did drop a double bond right here, we'd be able to say what? Pent 4-ene oic acid. Pent 4-N oic acid, enoic acid, right? En designating the double bond. Okay? Yeah? Very good. And I was thinking about the other day, you guys will always hold a very special place in my heart. You know why? You're my first batch of students ever. You guys are the first people I ever lectured to in my entire life. And I plan on teaching until the day I die. All right, what about this one? Aldehyde's the highest priority, right? We got 1, 2, 3, 4, 5, 6. Hex, right? And I sometimes when I was practicing or when I was starting out, I would do, like, I'd list them out in like parts and put the puzzle together. So I do hex, right? And then we got a 2 chloro in there, right? We've got a 5 bromo in there. We've got a 3 ene in there. And then we've got an anal in there. An al, right? Hexanal.
We have an anal in there. Don't laugh. Sorry.
That's the name of.
Wait, let's
right?
go
And I
back.
sometimes when I was practicing or when I was starting out,
Go
I
back,
would do,
let's go
like, I'd
back.
list them out in like parts and put the puzzle together. So I do hex, right? And then we got a 2 chloro in there, right? We've got a 5 bromo in there. We've got a 3 ene in there. And then we've got an anal in there. An al, right? Hexanal, because that's the name of an aldehyde. Hexanal. And now we can put it all together. Right? But if it's hex n and we have an ene in there, that's going to get replaced.
We can't
right?
focus
so now we
like
build from there.
this.
So hex 3 n al.
X3 and L. Oh.
And al. Very small distinction with the E and the A. But the number there designates that it's not going to be an A, because if it were an A, there'd be no number there. Correct? You guys know what I'm getting at? 2 chloro, 5 bromo, what comes first? Bromo's larger, and it's also alphabetically
Wait, say that again, bro.
an aldehyde. And then we've got an anal in there.
Anal.
An al, right? Hexanal, because that's the name of an aldehyde. Hexanal. And now we can put it all together, right? But if it's hex n and we have an ene in there, that's going to get replaced, right? So now we build from there. So hex 3 n al. And al. Very small distinction with the E and the A. But the number there designates that it's not going to be an A, because if it were an A, there'd be no number there. Correct? You guys know what I'm getting at? 2 E n al. And al. Very small distinction with the E and the A. But the number there designates that it's not going to be an A, because if it were an A, there'd be no number there. Correct? You guys know what I'm getting at? 2 chloro, 5 bromo, what comes first? Bromo's larger, and it's also alphabetically first. So 5 bromo, 2 chloro, sorry. 2 chloro, hex 3 E and L. Hex 3 E and L. 5 bromo, 2 chloro, hex 3 E and L. Yes? Yeah. I honestly don't remember, but I think you always go by alphabetical order. I had a debate on a TikTok like 2 years ago about size versus alphabetical order, and I think it's always alphabetical order, if I'm not mistaken. Right? Okay. Let's go over some special cases.
Size versus alphabetical.
So what do I mean by special cases? Because how was that? You guys...
Okay, I got all those questions wrong. Okay. I think I'll just. Okay. Wait. First off, let me type something out for you, okay? Monkeys eat. It's the way I studied. I feel like, at least for me, there's just so much I don't know that it would be like no surprise that I would have a bunch of gaps in my knowledge. Monkeys eat plenty bananas. Okay, do you see that? Monkeys eat plenty bananas. Monkeys eat plenty bananas, okay? Keep repeating that until the day you die. Because the first letters are going to be very, very important. It's the only things that don't follow, I think, Greek numbering. So, the first letters, right? M is for methyl. E is for ethyl. Not ethyl. Or maybe. Methane. Ethane. Oh no, it's ethyl? Okay. Wait. Methyl. Methyl. Propyl. Butyl. Methyl, ethyl, propyl, butyl. And then it goes on to like hex or pent, hex, 7. Hep, oct, non, dec, do, non, dec, dodec. After dodec. 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 Something. 12 is something. See, I don't even remember what 12 is. What is the Greek number for 12? Dodeca. Dodeca. Wait, what's 11 then? I thought dodec. Endeca. Dodeca? Deca. Not endeca, I don't think. Undeca? I don't think I've seen undeca. Yeah, undeca. Undeca. Not. Un literally means like no. Like undo. It's so stupid. Ugh. Well, I didn't remember that. Undeca. That's just the baseline for counting carbons. You need to know those prefixes for counting carbons. And then the rest is just all the functional groups. I need to review that. Let's see. For the functional groups, where is it? You know what? Functional groups and here we go. Okay. これはここ。Open image in new tab. ここ。How do I? You probably can't read this. Oh no. But carboxylic acid, anhydride, ester, amide, aldehyde, ketone, alcohol, alkene, alkyne, alkane. And then the suffix in order. Oic acid. Anhydride is just anhydride. Ester is O8. Amide, all, own. all in ein ein. If you want right now, we could. Do I have Microsoft Paint? Microsoft Paint. Here we go. Microsoft Paint open. Okay. Wait a minute. 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 Window capture. P. Okay. This is pretty good. Okay. Can you see this? 見て。これはOkay. I'm gonna do this for you, okay? Because this is like a test for me too, I guess. Somehow. Okay. So, this is a carb... 見てるか? Okay. This is a carboxylic acid, okay? Carboxylic acid is going to be this. This is a carboxylic acid. The most common one. Okay? COO8. Ku. Yeah. Ku. Yeah. And then for this one, for anhydride, right? Or actually, let's compare ketone with a carboxylic acid first, because I feel like it's really easy to mix up, okay? Ketones. Ketones are the same things as carbonyl groups. Carbonyl. And if you want to separate them, just remember carbonyl sounds like boner. This is a pure boner. Okay? It's a form of a boner. That's how you remember a ketone, okay? And then carboxylic acid, you do not have a bone in there. Got it? Got it? Okay. I can move on, okay? This is a carboxylic acid. The suffix is going to be oic. Oic acid. I hope I remember this. If I don't, I'm going to kill myself. I'm really going to kill myself. Oic acid. Okay, that's the suffix. That's the suffix for this. Carboxylic acids are king. They always win. Is it carbonyl group of stuff? Yeah, but a ketone is one of the most common. So that's how you separate carbonyls and carboxylic acids. Okay, anhydride is very beautiful. It's so symmetrical. I like to imagine it as two boners connected to each other. Two carbonyl groups connected to each other. That's an anhydride. It looks like some kind of monster. That's what I like to tell myself. Anhydride. Right is the suffix. Okay, we got that. Like all these are carbonyls? No. 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 No, 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 no. Carbonyls have to be terminal end groups. That's what I like to tell myself. But they are not all of these. All of these things in this group are not carbonyls. They've all got COs, yeah. But then it depends on where their placement is. I think. Ester? Gosh. I don't remember when Esther is. Esther looks like an Easter bunny, right? I remember Esther looks like Easter bunny, so it has to do something like this, I think? Like R group, R group. Maybe I'll fact check myself on that Esther group. Oh my god. I was wrong. That's an ether. Esther. One oxygen atom is double bonded. Ester is just carboxylic acid, but the final H is carbon chain or other stuff. It's just a carboxylic acid minus the H. Minus the H. わかってるよ. Okay. Do, do, do. What's it? This one is 08. 08. 08. 08. Okay. Stuck in the middle. Okay. And then, let's see. Amide is... It's just an H. Right? Amide is just this. Haha, yeah. Amide just ends with amide. This, think. Amide. 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 Aldehyde. My favorite. Anal. A boner with an anal. This, and then it just ends with an all. Is it not amide? You can think whatever you want. I call it amide. Amide. Yep. All. Dash all. Ketone. Beloved ketone. Ends with O-N-E. 1. Own. Own like bone. Bone. Alcohol. OH group. And it ends with OL. And then we have alkene. Just 2. Ends with E-N-E. E. Ene. Ein. Alkyl group is just ane. Ane, ene, ein. A-ene, ein. Alkane, alkene, alkyne. Hey. Yeah, that's that though. Okay. And then from this, those functional groups, right? Essentially what this is just IUPAC naming, because even though, what is it? IUPAC naming is still used because, you know this, chemicals can have the same connective or same molecular structure and stuff like that, but because their bonding is different, that could cause a lot of problems. So they needed a way to be able to figure out what chemical someone is talking about all the time, exactly the time. So this is the name you give it to be able to have a specific one. Not essentially what you do is you just number carbons, right? Number the carbons, try to find the longest carbon chain as possible, or find one that has the most substituents, and then you organize it by alphabetical order. And that's it. This is a carbon chain. Alkane, alkyne, alkane, alkane. Oh my god. See, I'm already getting sleepy. Normally I don't sleep at this time, but I'm getting sleepy because my brain does not want to study.
Get most of it correct? Did you guys kind of piece it together? Yes? Yes? Good. If you didn't, listen, if you didn't, I'll teach it from scratch. Tell me now. Do you guys want me to teach it to you? Yes or no?
Yes.
Yes or no? No? Okay. I'll make a video about it later if I have to. But these are my rules that I wrote down in my notes, which I haven't uploaded yet. I'm sorry, I will. Identify the parent chain, right?
Obtain? Yeah, obtain.
Identify the parent chain. Number the chain. Name the attachments. Assign those numbers to the attachments, and piece together the name. What do I mean by assign the numbers, right? If I have something like this, am I going to start numbering from the left or the right? From the left. Because that would give bromo 2 and chloro 3, rather than giving chloro 1, 2, 3, 4, and giving this 5. 1, 2, 3, 4, right? 5. Blah, 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 blah. Okay, so let's talk about some of these special cases. What happens when things that are functional groups are no longer highest priority? What happens, right? So let's talk about going up in oxidation, as we always do. This is a alcohol, and this is ethane, so it's ethane, but it's an alcohol, so it's ethanol, right? Ethanol. What happens when the alcohol is no longer the main attraction? So let's say that we have a ketone, or an aldehyde, right? Let's do an aldehyde. 1, 2, 3, 4. So this is what? Butanal, right? Butanal. Aldehyde. AL ended, right? Who knows the NMR peak for an aldehyde? It's like way out there. It's like 10 or something, or 9. It's past the benzene ring, I know that. Right? Butanal. And then if we put an OH on this, who knows what that's called now? That's called what? Say it louder. You're right, say it louder. Hydroxy. This is 1, 2, 3, hydroxy, butanal. Yes? Project. Trust me, the mic's not gonna hear you, I am. 3 hydroxy butanal. All right. I love this example. Hee hee hee.
So we look for the numbers?
Yeah, but the numbers was, well, what's higher priority? Aldehyde or ketone? Ketone, aldehyde, aldehyde, aldehyde. Aldehyde. Aldehyde is higher priority. Why? Why is the aldehyde higher priority? The aldehyde is a chain terminator. It stops. There's nothing after the aldehyde. You are done, right? Because after a ketone, you can keep moving, right? But an aldehyde says, done. That's the end of the molecule right there. So this has to be number 1. Schmidt-Werber-Mengerman-Jensen. That's the aldehyde. He was number 1, right? You get that reference?
Aldehyde.
Yeah? SpongeBob? You know SpongeBob as a kid? You remember the episode where he finds the dude's hat? It says the number 1 has a little soda thing inside of it, and it says number 1 on it, and then Mr. Krabs like trying to pawn the hat, and he's like, Schmidt-Werber-Mengerman-Jensen. You guys, go home, go look it up. You guys are terrible. You're the worst. Okay, look. Schmidt-Werber-Mengerman-Jensen. You go home, you look that up. Schmidt-Werber-Mengerman-Jensen. He was number 1. You watch the whole damn episode. You know what? That's your homework. Watch this goddamn episode of SpongeBob. Yo, I got the most out-of-pocket comment on my TikTok yesterday. I posted a snippet of our lecture from last time, the one where I was doing the radical resonance and everything. You guys remember how before I taught that, I was like, put your pencils down, just like look at the board, you don't even copy this down. So none of you were writing anything, right? I posted those like 9.5, 10 minutes of lecture on my TikTok about the radicals and tyrosine, the glutathione, blah, blah, blah. Some fuckhead comments on my TikTok and he's just like, first of all, he's like, great content, but bro speaks too fast for students to take notes. That's fine, I don't mind that he said that. But then the next thing he said was, and he seems like an unlikable person. I was like, yo, I would honestly rather you call me a slur at that point. Like, just be openly racist. Like, I think that'd be better than calling me a unlikable person.
You should not be admitting this. He's yapping too much. No, I find it kind of funny though. I love how he's like, well, I mean, for someone who's in a rush, right? It's not fun, but like, I love how he adds these little anecdotes. It makes his lectures more memorable to me. I can skip it though, if you'd like. But it's crazy. Why would you admit that out loud, man? Oh my god.
Based on me lecturing to my students. This is a TikTok comment, guys. It's fucking crazy. It's the funniest thing ever. So I got on this whole like fucking TikTok argument debate thing. Not even. I think Kevin literally just replied and said like, lol, your mom. It was so fucking funny. So this guy, I'm telling all my friends about this fucking comment I got on TikTok, and meanwhile Kevin's in the background fucking having an internet feud, fucking Twitter fingers with this guy behind my back. And the thing is, my friend Kevin has a very low-key TikTok.
I'm just here to learn.
Kevin's just fucking going off on this yesterday. Anyways, back to the content. So like we said, the aldehyde is Schmidt-Werber-Mengerman-Jensen, and he was number 1, right? And we number from the left over there. What happens when a ketone or an aldehyde isn't highest priority? What do we call it? Not a lot of people remember this because it doesn't really come up all that often. It's called an oxo group. So we have a 4-oxo substituent on this. And now we make this 4-oxo pentanal. 4-oxo pentanal.
Okay.
Let's do one more. And then we'll talk about special, so those are like when cases when higher priority things are not high priority. Then we'll talk about special substituents. That's tough. 1, 4. 1, 2, 3, 4.
Wait. I want to do this. I want to do this. I'll walk through this. Bum, 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 bum. H. I want to do this. Okay. I'll actually get this one right. Okay. 1, 2, 3, 4. Okay, there's 4 carbons, right? That's gonna be 2 bute. Okay. And since there's a carboxylic acid, the ending is gonna be toic acid. And then since there's 2 of them, then what you're gonna do is put, is it? I think you can do 1, 4. 1, 4 butoic acid. Does that make sense? Because there's 1, 2, 3, 4. There's 4 carbons, so that's gonna make this a butane. And then since there's carboxylic acid, then the suffix, you have to take the ane and replace it with the OIC ACID oic acid. Then you're gonna have butoic acid, but then you have to number like which ends the or actually why don't you add in the numbers though? Well, actually no, you wouldn't add in numbers to the front, like the di, tri, like that, because they're not on the same one. Yeah. Locking in my answer, 1, 4 butoic acid. 1, 4 butoic acid. Did I get that?
1, 4.
1, 4. Did I
1, 2,
get
3,
it?
4.
1, 2,
So
3,
somewhere in
4.
there is going to be a bute. I think it's like, I honestly don't know. The reason I brought this up is like 1, 4 butane di something. Butane dioic acid. But di because 2. But hold on before you write that down. We have special names for these. There's a few of them that you have to know.
Wait,
This one,
di?
you might not recognize like this, but you might recognize like this, the way it appears in the body.
But it seems to be wrong. Dioic, right? Dioic. Cause the thing is, I thought you had to add that number in only when there's some like on the same what's the word? Same carbon? Yeah. They have to be on the same carbon, but I guess in this case, why don't I just Google that? When do you add a number prefix, a Greek number prefix to the front of a family of a priority group? Priority. When do you add a Greek number prefix in IUPAC naming? Question mark. If a molecule contains 2 OH groups acting as substituents, e.g. in a compound with a ketone that has a higher priority group, the prefix is dihydroxy. For simple chains or functional groups like chloro, methyl, or hydrox. The molecule has multiple substituent functional groups. Huh. So as long as you have something identical, you just have to include it, regardless. Even if they're in different spots. Interesting.
This is succinate, otherwise known as the anion of succinic acid. I hate it too, man, don't worry. Oh my, such good apples. Who knows who taught me that? Professor Malitsky. Each of these stands for the number of carbons that you have between carboxylic acid groups. This is 0, 1, 2, 3, and 4. And you should know these by heart. I no longer do, but you should, because they might come up. But the two that you really should know, and the two that we'll talk about right now, are O and such. O and such. So
Krebs cycle?
O means there's 0 carbons in between carboxylic acid groups, right? This is oxalic acid. Why is this important? It is the precursor to oxalate, which is found in your body and can precipitate calcium oxalate kidney stones. It is also one component of oxaloacetate, or OAA. This is oxalic acid, the O in Oh My Such Good Apples.
Whoa.
Such, like we said, is succinic acid, which I will draw as succinate. Succinic acid. I don't remember what G and A are, but I believe M is maleic acid, I think. I can check that. I think you guys have a pre-lab on maleic acid, actually, this week. You guys are doing the bromination of maleic acid in Orgo. You did it already? Okay. It is 1, 2, 3, 4.
Maybe I should have
Hold on.
watched
That's not correct.
biology
it
before
malic acid?
this. Huh.
It is not malic acid. I don't remember what it is. Hold on. Malonic acid. It is malonic acid. I actually have them all here right now. So, oxalic,
I don't really remember much
Malonic?
of bio.
succinic. What is that? Glutaric, I believe? Glutaric and addictive. Don't confuse glutaric acid with glutamic acid. What is glutamic acid? It's an amino acid, glutamate, correct? Yeah? Oh my such good apples. You will only really ever come across 0 and 2. Now, why did I bring up oxalic acid? Well, in the citric acid cycle, because you guys know I love to overteach, right? In the citric acid cycle, we have a precursor, or an intermediate known as OAA, which gets the whole party started. And when you take OAA and you add X, you get citrate. Who knows what the X is?
What the
When you add X
fuck?
to OAA, you get citrate.
Why are you
What's the
trying to
X?
teach me bio, man?
Got it.
Isn't
It's
this
a
an
pyruvate. It's a
OCHEM
derivative of pyruvate.
lecture?
What does pyruvate turn into? What do we do with pyruvate? What do we turn it into? Acetyl-CoA. Also, acetyl-CoA, in the sake of shorthanding all your notes, you're going to write it a lot, A-CoA. A-CoA is acetyl-CoA. Okay, so we take acetyl-CoA, and we add it to oxalate, and we get this molecule.
Wait, but the OTR, I don't even know what the citric acid cycle
Hold
is
on.
for.
Rusty. That's
I
better.
forgot.
That is.
Is it citric acid
Citrate.
cycle the dark
So I
cycle?
call it the citric acid cycle or the TCA
Or
cycle. But
TCA.
TCA doesn't stand for the citric
No.
acid. What does it stand for? Tricarboxylic acid. 1, 2, 3. Tricarboxylic acid. So what are we adding this to in order to get citrate?
Oh, this is
We're adding it
hard,
to
man.
oxaloacetate.
Is the cycle that
Do you
makes
see
your
the oxalo group?
ATP citric
Oxalo?
acid? Why did I say
Oxalo?
citric acid? Yeah,
Acid.
citric acid cycle.
Oxaloacetate.
That makes your ATP?
2 parts. Does that make sense?
Ah.
So now, since you know how to name them, you'll never forget how to draw them. Because you know acetic acid, or acetate, and you know oxalic acid, or oxalate. And if you put them together in a synthesis, in a dehydration synthesis, you take away one of their O minus groups, you will get an oxalate attached to an acetate, which is oxalic acid. Oop. Did I fuck up? I think I fucked up. That way. Oxaloacetate. I missed a carbon. Making sure. That is right. Oxaloacetate.
36?
Oxaloacetate. That make sense? Yeah. Oxaloacetate is a 4-carbon structure. Citrate is a 6-carbon structure. By the end of the citric acid cycle, we will reform oxaloacetate. Who knows where the other 2 carbons go? Carbon dioxide. Very good. 2 molecules of carbon dioxide. All right. So those are your diacids. And now we're going to talk about some special attachments and special groups that can occur on certain molecules. The number one thing, the first thing I want you to know is what this thing is called. What's that called? Phenol. And I told you when I gave you a pKa table
Phenol.
that alcohols generally have a pK between 14 and 16, right? Or sorry, no,
Phenol.
16 and 18. Right? Generally, alcohols have a pKa between 16 and 18. What's the pKa of phenol? Huh? 10. How'd you know that? It is 10. It's 10.4. Very good. I don't have Jolly Ranchers with me. I'll eat one. Remind me next time. And you too. Phenol with a pKa of 10.4. Why? Why is the pKa of phenol so much lower than the pKa of other alcohols? Well, first of all, does low pKa mean more acidic or less acidic? And what makes something more acidic? Conjugate base? Stability. Right? So let's write phenol as a base. Let's put it in water and write it as a base. It makes sense, right? Because one of the things that stabilizes conjugate bases is resonance. Very good. Very good. And this is called what? Orgo people, this is called an aromatic transition, correct? To get the ring to flip. Ah, yes, that's why it's so much more stable. Yeah. It would depend on how much resonance you're getting out of it, but because it's going to a benzene ring, you get quite a good degree of acidity. Alright, because that's called phenol. It's a very special alcohol. Alright. You're gonna know this one, and you will know this one. I expect you to know this one. What is this called? It's part of ubiquinone, right? It's part of ubiquinone, but I'm not gonna call ubiquinone yet. I'm fact-checking my information, like I always should, because I don't know everything. That is true. This is called a hydroquinone. If that's called a hydroquinone, orgo people, what's a quinone? Well, the hydro, it comes with what? It comes with electrons, right? So if we oxidize this, we would probably get a quinone. And if you oxidize a benzene ring, like this, you get a very special structure. And this is a quinone. That's a quinone. Hydroquinone and quinone, right? And these are just oxidations and reductions of one another. Ox, red. This is very important to complex 1, complex 2, and especially complex 3 of the citric acid cycle. Because inside of your body, you have a
That's
coenzyme
so
called
scary.
coenzyme
Why is
Q.
biology
And
coming
coenzyme
into
Q
this?
has a hydroquinone/quinone group, which is
Just kidding, I
capable
knew
of
how it's fucking
carrying
related to each other
electrons,
because
which is why it's included in the electron
essentially
transport chain.
the
So what happens in the electron transport chain
explanation
is that
for
Q
bio
gets
stuff,
turned
but
into
then why is he lecturing
QH2.
about
And of course, because the
bio?
hydrogens come with electrons. So that means that this is getting reduced,
I don't like
right? What's it getting reduced by?
Oh,
Other electron
싫어요.
carriers like NADH. And reforming NAD+. This is the
싫어,
goal
싫어,
of complex
싫어.
1.
I don't like it.
And it all starts in orgo, learning how the oxidations and reductions and naming and everything works. Because if someone came up to you and they're like, oh, well, complex 1, that's just turning a hydroquinone into a quinone into a hydroquinone, and then the NADH, blah, 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 blah. Like, what the fuck are you talking about, dude? What are you saying? No, but now you know that the hydroquinone carries electrons, and the quinone receives electrons.
The bio?
Which would kind of make these, like,
TR, let
Lewis
me
acids
steal
and
your
Lewis bases,
brain.
right?
I hate
Kind of.
bio. Ironically
Nudge.
enough.
That everything's an acid-based theory. Right, cool. Even redox chemistry is acid-based theory, isn't that crazy? Any other, like, special groups I want to tell you guys about? Special, like, this is, like, fine.
You're talking
We'll do
about
this and we'll
mead.
How do you name it? I don't
Amine.
expect you to know how. This is called N,N-dimethylamine.
What the fuck?
And you may see in the passage. I doubt they'll actually name this straight up by itself. But it's called N,N-dimethylamine because the dimethyl groups both exist on the nitrogen. N,N-dimethylamine. And this would be N-methyl.
No, don't
N-ethyl,
say
N-methyl,
that.
methylamine.
Why are you saying that, man?
Oh, sorry. N-ethyl, N-methyl, ethylamine. Right, because ethylamine, why is it ethylamine? Because there's 2 carbons here on the...
Do you know how freaking powerful your goddamn brain is? You know how powerful... You know how powerful your brain is? Pause. We need to talk about this. Do you realize how freaking crazy your fucking brain is? Do you ever think about the fact that it's like, why are you still breathing right now? Can you think about the fact that you don't have to think about you breathing? Why you're conscious and able to watch me and process what I'm saying to you right now? Why you're able to visualize this 2D anime girl on your screen? Was that you're just older now? No. Age is just a number. Age is just a number, OTR. Now. Ooh. I consciously breathe is such a funny thing to say. I can't say that. Well, I just said it though.
Fuck. Even I'm fucking myself up. Start over. This is an amide. This is N,N-diethylamide. This is N-ethyl N-methyl ethylamide. Right? Because
He's
this
rapping.
is ethylamide.
He's rapping.
And then you just name the
He's
substituents based on how they connect.
rapping.
Does that make sense? Sorry for confusing you. One more thing. Oh, yes. And before we do chapter 5, which we'll do today, I will show you guys the whole carboxylic acid derivative thing that I was talking about, like the leaving groups and everything. Very important. Very important. But the reason I got reminded of that is because a lot of people don't know what this is. What is this called? The group by itself.
Anhydride.
This group. It looks like 2 carboxylic acids had sex, right? That's basically what it is. You form this by synthesizing or reacting 2 carboxylic acids together. Do you know what it is? It's called an anhydride. It's called an anhydride, right? and then hybrid. So how would we
Two
make that?
Carpix.
Orgo people, Hercules, this is
Two
really important, especially on exams. They
carboxylic
want you to know how to do
acid
this.
groups
You need
had
to take
sex.
a carboxylic acid,
Such
make it
a
a solution
funny
of basically itself,
way of
right?
saying
This
it.
this chemistry is really fucky. It's really, really fucky chemistry. So watch the whole time. You take it and you acidify it, usually with a pretty strong acid. You use catalytic amounts of H2SO4. And what happens is that the H2SO4 performs a protonation effect. It performs a protonation step on, like we always do, the carbonyl oxygen, because that's how we get TCAI started, tetrahedral carbonyl addition intermediates, right? Now, between this and that, which oxygen is more nucleophilic? This is like a level 3 question about what I've told you so far about these specific things. Which one's more nucleophilic? This guy or that guy? Which one?
That guy?
This one? All right, we got one vote for that guy. Guys, everyone vote. Who's more nucleophilic, A or B? All right, we got one vote for B. Who else? A. B. B? A? You guys are trying to like make it even or something? No. It is B. Why is it B? Guys, all right, I'm going to castrate someone if you guys don't say this properly. P orbitals are electronegative. What's here? P orbitals, they're detracting from the nucleophilicity of those electrons. There's not the same p orbital density here, thus that oxygen would become more electronegative. Because this is an sp2 oxygen, it has more S character, known as a fucking p orbital, right? So it's attracting the electrons over there, right? And it's decreasing the nucleophilicity. So if this electron is more nucleophilic, it's going to perform the attack.
I
You have to
think
learn to
it's
draw
like
backwards. Draw
the ability
backwards.
to attract stuff to the nucleus.
Attack the vulnerable carbonyl position. This is where it starts to get a little fucky. Sucks, right? That does not look fun. And the thing is, you're actually not, so obviously the Orgo people realize that we're about to kick one of these off, right? But you're not allowed to transfer within the molecule. Why? Because you would make a 1, 2, 3, 4-member transfer ring, and 4-member rings are not good. So what actually happens is that a molecule of the solvent will pick that up and then drop it off somewhere else. But we're just going to show it simply as a proton transfer. And I'm just going to write 2 steps. Because you can't do a 4-member proton transfer ring. Professor Melissy very much told me that that's not allowed. All right. So when we do the proton transfer, one of those, I'm going to put this up here, one of those is going to become protonated.
It's just some reaction
We get O
stuff,
and
man.
H,
I think
and
he'll
we get
teach
O,
it properly later
Oh,
on.
fuck, anyways. There we go. Learn how to draw upside down. And now, what the fuck? What did I do? Sorry. There you go. Yes? And now, electrons stream down and kick off, and you get this. And that gets picked up by someone else, and you will make an anhydride. This is really fucky chemistry. Probably won't show up on the MCAT, but I want you to know how they're synthesized, because A, I'm over-teaching, and B, I'm prepping you for Orgo 2 as well, because a lot of you guys are taking that, and you need to know how carboxylic acid derivatives are formed. Helpful? Can you follow along? Very good.
You can ignore
Done?
this. He just said
Anyone want to
that.
take a picture?
Unless you want to
Take
be a
photo, take photos.
tryhard. You want to be like
Oh,
Northern
dude, what the fuck? My
Lion.
markers are right here.
You want to be like
Who's been
Northern
using my
Lion
markers?
and do
I'm
the
gonna castrate them.
ungraded optional assignment.
Not a doctor yet? Oh, trust me, I've heard doctors say
I
worse.
think I just do for questions.
I think that's
no!
it for nomenclature. If you guys are okay, any questions about anything we said? Nomenclature really comes with practice. Oh, all right. Trans, cis, also E and Z, correct? E and Z. Very good. Okay, now we're done with nomenclature. You do. We're gonna do chirality. There's like gonna be a whole lecture on that. Don't worry about it. So tune in soon for chirality. Thank you guys for watching. Let's take a break. We are live. Welcome back. We're gonna talk about isomers. Sarah was making me laugh, so we had to re-record this.
Isomer. Wow, we finished. We finished one. That's awesome. We're so cool. We're so freaking cool. Yay! Yay! Hey, so back at it again, right? I think forgot all my functional groups. Oh my god. Oh my god. We need to. Come on. OTR, I'm gonna have you try to keep me accountable right now. Okay? Let's. I have them, yeah, but I'm a little bit scared to start the practice questions. And I also think I can't do them without getting bonked by AAMC. Am I famous enough for them to do that? Do they gaff? Do they gaff like that? Let's try to do this for the night. And it might actually, because I feel bad. Why are you awake? Isn't it like 4 a.m. for you, bro? What the hell? What the frick? But I think it's really important that we get our functional groups down. So I'm gonna try this, okay? I would if I could though, honestly, screw them. Like, what the hell, dude? You guys hate poor people. you hate poor people, you know? Like okay. Um Sorry for my messy handwriting. Starbucks thick as okay, carboxylic acid. The structure is boop 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 boop. Carboxylic acid. This the suffix or shoot, I do not remember what the prefix. I do know the suffix though is oic acid, right? Anhydride. 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 Anhydride is boop boop two carboxylic acids that had sex. Not forget that. Two carboxylic acids that had sex and made a monster. Okay, so that's gonna be anhydride. And I'm gonna have to go back and try to remember the prefixes too in the scenario that the AMC decides to be mean. 32? Do you have work? I'm sorry. I'm so sorry. Oh, the Okoko? I'm not gonna remember Okoko, man. Okoko. Hydride. And Esther. Esther, like you said, right? It's just a carboxylic acid, but without the H. So, just this, essentially. Attached to whatever R group. Then for Esther, the ending is 8. 8. 8. Oh, sorry. Not 8. It's OH, right? 08. For a ketone, it's this. Our boner. Our boner. And then 1. Right? And then for an aldehyde, remember anal. Aldehyde. Aldehyde is oh oh shoot aldehyde own ill what is aldehyde? Oh no, I don't remember aldehyde. Is it ill? I think it's ill. I'm gonna go ill. Wait, no. It's for an alcohol, right? Chart. Start. Start. Wait, anal, 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 anal. Oh my gosh, I can't believe I forgot about the anal. I could wake up and study. Is your schedule like 4 to 9? Like 4 a.m. to 9 p.m.? めっちゃいいですね。めっちゃいい、めっちゃいい。What time do you have work at? わからん 9? 对的，我根本头发。哇 That's only 3 hours of sleep though. What the heck? Worry about me? Okay. I think I got it, right? Did I get it? Like when I get tired. All own. Oh wait. Did I get it right? OTR, can you check? They look right? They look right is not the same as they are right though. Can you check? Check for me, please? Or maybe I could check myself, but I feel good depending on you. And asking you to help me. これどうですかのこの Am I missing any? Carboxylic acid, anhydride, ester, ketone, aldehyde. And I think I'm missing the last ones, where it's just alkene, alkyne, alkyne, and amide, which is just amide. Check for me, OTR. Please, please, please. Please, 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 check for me. In. Still. Hide. Okay, thank you. Thank you. Thank you. What about ethers? I don't think we have to know about ethers, to be honest. Ethers never really show up as substituent groups because they're kind of strange. Yeah, ethers are kind of strange. Unless, do you know what's an ether? What's the suffix for an ether group? Suffix for an ether group, or yeah, the suffix. I don't know. OTR. Tell me, tell me, tell me. Oxy? Okay. Wait, let's get back on it. Back on this. Hold on. Here. Open this. Oh. Give me the photo, woman. Give me the photo. Give me the photo. Man! Man! Why won't you let me in so bad? Take a show. Take a show. Okay. Everything looks right? Yay! Okay. Oh, I forgot alcohol. Don't forget alcohol, OTR. Alcohol is dash OL. OL, OL, OL. OL, OL. Okay, OL. Don't forget that. We forgot alcohol. Because I'm silly. propanol, ethanol, oil, and alcohol. Well, I forgot it. I didn't even remember alcohol was a. I can't drink. I don't know how to drink. I love ethanol. Stop it. Get some help. You have an addiction. Okay, let's write it down. Okay. Okay. Carboxylic acid. Right. There. Aldehyde. Uh, Fine. Every time I spray 70% ethanol to wipe down stuff, it smells so good though. Dude, it burns my eyes. I like hate it. It makes my eyes sting. I also don't like the way it like makes my gloves feel. I know this doesn't happen, but I get paranoid that it'll like burn through my gloves. But that's benzyl alcohol, not ethanol, really. Ain, oh, oh, own. Wait. Oh, all your hand sanitizers? Oh, nice. Okay. Mm-mm. Okay. Okay. CARBOY, carboxy. I tried this again. Block the carbonyl. Carbonyl. Oil. 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 Can oil lock carbonyl? cock or onion? No, wait. No. Cardamom oil. Oh. Okay. But, okay. I watched this video on isomers pH, but you wanna go through it still? Um, the the thing about isomers, right? I think it will become more important with reactions later on, just because there's you know how there's like what I said earlier. You need IUPAC, right? Because sometimes you'll have molecules with the same. I'm horrible at finding chiral centers. Ah, you kind of have to just remember. See, that's the catch, though. You need to know what functional groups are and what they look like, because chiral centers are just four different substituents, right? As long as you have four different substituents, you're pretty much automatically guaranteed to have a chiral center. Mm. They have to be four different ones from each other. Yeah. Uh, this just becomes important later on when you're doing reactions, though, because even though some molecules have the same molecular formula, their connectivity might be different, and then sometimes you can rotate bonds, but other times you can't rotate them, and you have to break them to be able to like have two compounds be in the same like configuration, like same position. Yeah, but that's a whole other can of worms. uh, Maybe I should just watch the video and not take notes. Just enjoy.
We are live. Welcome back. Happy Halloween. And what a great day to begin our studies of organic chemistry. I'm having some problems with my YouTube. We're getting the general chemistry videos up as we speak. I have chapter 1, chapter 2 uploaded. Chapter 3, 4, 5 should be soon, and then the rest of them. Because we all have them all recorded except for chapter 8, because I can't teach chapter 8. Bad, right? So today we're going to gloss over. So we're going to do chapter 3, 4 of organic chemistry. And when I have a bit more time, when I'm out of my exam week, we're going to go back to chapter 1 and 2, do a full deep dive of all that. Because most of the people in the room know nomenclature, but I know some of the people back home might want some help. Or maybe you guys just wanted like a little refresher. We'll do that later, but I would rather use today to go over some stuff that is more relevant to the chemistry we just covered and more intensive and a better use of my time. Okay? So we're gonna do chapter 3 and chapter 4. So chapter 3 is very short, it's bonding.
Yeah, bonding.
And there's very, very few things that are super, super important inside of the bonding chapter, right? So number 1, we want to go back and recall our, you guys hear that? That's weird.
Hear what?
We want to go back and recall our atomic orbitals and quantum numbers, right?
Oh, hell no.
So our N, L,
Where's
M, L,
What the
and
fuck?
MS, right?
Why is he
So remember that
doing
the N was the
chemistry to
energy
this?
level.
Oh, hell no, bruh.
That the L was the sub-level. The ML was the orbital.
Orbital.
Or sorry, no. L was the orbital. My bad. ML was the sublevel of the orbital. And MS was the spin of a specific electron inside of a
Yeah, but I want my organic chemistry,
Atom,
man. My
right, an
carbon
atom.
shit, not this theoretical fucking electron bullshit, energy, whatever. Ew.
So
Ew.
this is not something that has been super explained super well to anyone, including myself. And basically what happens is that atomic orbitals bond to form molecular orbitals. And this is the backbone of molecular orbital theory. And if the functions are the same, they form a bonding molecular orbital. And if the wave functions are opposite, they form an anti-bonding orbital, right? So if you have an s orbital like this and an s orbital like this, and they bond, you will get a molecular orbital like this, right? They come into a bond, right? Cool? And then if you get a s orbital like this and an s orbital like this, in phase, out of phase, positive, negative, whatever you want to call it, right? They will antibond. And this is just what the book is telling me. Like this is verbatim what I was taught from my organic chemistry professors, right? But this has an important correlation here, right? An s and a p orbital can bond in this fashion. And a p and a p orbital can bond in this fashion.
Uh-huh.
So this is called head-on, right? For the p
Head-on
orbitals.
collision.
And what kind of bond do you think that is between the p orbitals, if we were to classify the type of bond? That's a sigma bond. This is a sigma bond. This is
Sigma.
a sigma bond, right? Remember, this is the anti-bonding. We put a star there, right?
Sigma. Sigma bonding.
But what does a pi bond look like?
I bond.
How do we form pi bonds? Well, pi bonds happen when we take a p orbital, right? And we put it next to another p orbital in phase. And they bond over one another. And they're going to give you something that looks like the best of my artistic ability. Something that looks like this. And that's going to be your
I feel like
pi
that's
bond.
the structure that
right?
you get on like
And then it's possible that inside of like this, if we were to
Western
draw something
blotting or
like
something
this,
like
right?
PCR.
We're able to illustrate this in a
Not Western
meaningful
blotting,
way.
like PCR.
right? We're able to illustrate this in a meaningful way,
What is that?
where we have
What?
the carbon,
Sigma alpha.
which has a p orbital like this, and this carbon that has a p orbital like this, and they bond over one another like that, and they form that pi bond. And then we're going to have a sigma bond over here. And remember that in these bonds, these are very simplified, but in this molecule specifically, it's going to be, what are the orbitals here, the ones that are bonding over there? They're sp2 hybrid orbitals. So we talk a little bit about hybridization as well. Do you guys recall that from general chemistry? Like, not general chemistry from the MCAT, because they're not going to ask it of you, but it's just good to know that when this forms bonds, right, the pi bond of the double bond is formed by the lone p orbitals, but the rest, the trigonal planarity of the other bonds, is formed because the carbon has 1, 2, 3 hybrid orbitals, correct? That is a hybridization, that's what hybridization means, of an s orbital and 2 p orbitals. Does that make sense? It's called sp2, right?
Yeah.
Okay. So I didn't take a lot of notes for this chapter, mostly because there's not that many to take, but one thing we do need to talk about is hybridization and resonance, okay? So we're gonna do a little touch on resonance because we're gonna do more resonance when we get to actual, like, acid stability, base stability, blah, 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 blah. We're gonna do a lot of that, right?
Okay.
But let's just touch on it real quick.
Resonance, my favorite. Oh my god.
I think we should do like it's not in the book, but I feel like we should do a lecture on resonance. Okay, it would be really helpful because I feel like a lot of people don't really fully understand what resonance is.
They
Like, I'm
don't.
sure you guys know how to do it, but do you know
Resonance is
how
hard,
it works?
man.
And like the biochemical applications of resonance
Resonance is
as well,
really freaking hard.
right? So like we could definitely do that. I feel like I want to make that a lecture.
I remember
like
okay was
aside
really
from what's in the
freaking
book.
brutal. Because we would
So-
always have to draw resonance structures on exams and stuff like that, and then
Speaking of hybridization,
professor
let's go over my trick again.
would be
right?
so hard.
So what counts as an electron domain? Does anyone remember?
Struggling with MCAT cars?
Shall we? No, I'm not struggling with it. No. Stop it. Get some help. Yeah, like I was saying though, my professor, they're very strict about like what was like a realistic resonance structure simply because like well they're like on top of like teaching they're also experimenters, right? And they're just really stickler about that, man. Oh, yeah. Trying to give a kid like 5 minutes to try to think of like 5 resonance structures might be a little bit difficult. Maybe less than 5 minutes, more like 2 minutes. 2 minutes to come up with 5 resonance structures. I don't know.
We got double bonds. We got triple bonds.
Bonds.
And we got lone pairs. And all of these count as how
You
many
don't
electron
remember what
domains?
resonance structures are?
1.
Resonance structures are essentially like if you move
Let's
electrons.
throw some examples on the board.
Yeah, it's just
right?
double bond shifting
What's
around
the
essentially. Or if you
hybridization
take an electron,
of this
then you take it and use it to form a bond. And then what
SP3,
happens to the
right?
structure?
And how would you do this with my
And
little trick,
sometimes-
right? So always,
or
the way
I
I
think
think
it's
about it, throw
because,
down the letters. You got an s orbital and 3
is
p
it?
orbitals, right?
Molecules.
For every electron domain, you go
they
1,
actually
2,
don't stay
3,
in one
4.
form.
You go
Or
1,
compounds,
2,
I mean.
3,
They
4.
don't
How
always
many
stay
s's
in
did I
one
use? I used the
form
1.
constantly.
How many p's
They're
did I
always
use? I used
interchanging,
3.
And depending on how
SP3.
frequently they
Right?
interchange
Let's
and
do another example.
what kind of structure they originally had, sometimes they're more
What's the
unstable.
hybridization of
That's
this
essentially
guy?
what resonance is. Resonance kind of determines whether or not something is able to
That guy.
react. The reactivity.
SP2. Why?
I thought it was
Throw
really
down your
cool.
letters. 1, 2, 3. 1, 2, 3. We used S and how many P's? 2. What's that lone P doing right there? It represents the P orbital that is participating in the pi bond between the carbon and the oxygen. Right? That's going to become important when we talk about resonance. That P orbital that exists inside the sp2 carbon. Right? Okay. Let's do another example.
2, 3.
Don't get scared by the charge. Same rules apply.
Is it sp2 still?
1, 2, 3.
sp2.
sp2 with a lone p orbital. And that is the p
sp2.
orbital.
Oh,
That
okay.
what? When we form a carbocation inside of an SN1 reaction, that is the p orbital that the water or the solvent will attack and attach to, right? That's that p orbital. Let's do another one. I'm going to do 2 more. That guy.
That guy. That guy. Uh-huh.
Throw down your letters.
So down my
1,
letters
2,
too.
3. 1, 2, 3. We've got sp2 and a lone p orbital. And that lone p orbital does what? What's that p orbital doing? Pi bond with the carbon, right? How you doing? Pi bond with the carbon. All right, last example.
But that's pretty cool. Cool.
I want you guys
The
to really
electrons
focus
count.
for this one.
That was sp2
The carbon.
then,
All right,
right?
last example.
Yeah. Oh, okay, the electrons. The pi bond
Pi-
still counts as
I
1.
want you guys to really focus for this one.
Okay.
You're not allowed to talk. Give me the hybridization of that guy.
1, 2.
Let's do my trick, right? So let's draw him out and let's do my trick.
Yeah. Is it sp3? I think it's sp3.
1, 2, 3, 4. sp3. Simple enough, right?
sp3, yeah.
Except if that were sp3, we'd all be dead.
Oh, what?
That nitrogen is not sp3.
It's not?
That nitrogen is sp2.
Why is it sp2?
How?
Yeah.
David?
Is it resonance?
Where? Where's the There you go. All right. So nitrogen with a lone pair bonded to an sp2 species, specifically a carbon, will always, for this exam, always resonate.
Oh.
It's a lone pair.
Okay.
Always.
Why?
And that's why I left
This
this
is
for the end, because I
stability.
want it to be our segue into resonance.
Oh, you're so smart.
Resonance
Don't be
bracket.
sarcastic.
The electrons
I'll
go
kill you.
here.
I'll skin you
right? They go
alive.
toward what? They go toward the p orbitals. Right? Where are the p orbitals here? Here and here. So they go toward the p orbitals. Carbon can't accommodate that many bonds. The bond breaks up towards the oxygen. Resonance arrows. We made a double bond to the
I'm not
NH2.
being
It
sarcastic.
accommodates another bond, so
Yeah,
it gets
like
a
the
positive
story.
charge. And we break
That's what my mom
electrons
said.
up toward the oxygen, and we drop down.
That's what my mom said when
And
she gave birth
since
to
it
me.
participates in resonance, in this structure it looks sp3, and in this structure it looks sp2.
But
So
is it?
which one is it?
That's what my mom said to me.
It
when she
must be
said I was
sp2.
not adopted.
Because if it were sp3, it wouldn't be able to look like that ever. Right? So if something even has 1% sp2, if it has 5% sp, it must be sp2. It has to be. Does that make sense? Yeah? And I believe, if my memory doesn't fail me, like Professor Malitsky told me, that this actually happens like 60-40. 60-40, 70-30, something like that, right? I'm not 100% sure. You know, I'm not a quantum chemist or anything like that. I wish I was. That'd be cool, right? Okay, so that's our little introduction to resonance. Now, what did we learn? This is a very, very important thing right here. Because what did we learn about resonance from this specific thing?
Stability.
From this specific little task? Well, number one,
Stability.
that proteins in our body are stabilized by those bonds.
Yeah.
Right? Because those are the amide
Protein.
bonds. If we have amino
Whoa.
acids,
Yeah. Whoa. Okay. Protein.
N bond sp2, N bond sp2, N bond sp2. All those nitrogens are resonating their electrons into that sp2 position.
Yeah.
Meaning that peptide bonds inside of our body are ridiculously strong because of the fact that the nitrogen has sp2 character, that it is sp2.
Whoa.
Understood?
Okay.
And this also allows for the structural dynamics of proteins. When proteins fold and they interact with one another and blah, 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 whatever it is, it folds according to the planarity of this bond. What do I mean by the planarity of the bond? Well, if it's sp2, then what's the shape? It's trigonal planar.
Oh, hell no.
And that means that the bond is flat about that
Trigonal planar.
axis. Correct? And if the bond is flat about that axis, you can imagine that this might be 3D, but over here it's flat. And this might be 3D, but over here it's flat. And it's flat, and it's flat. And it goes like that along the whole length of the protein. Does that make sense? Yeah? Okay, cool. And that also contributes to what? The stability of proteins themselves.
You're
The stability of proteins themselves, why we need enzymes and why we need a bunch of energy in order to break peptide bonds. So number one is proteins. And number two, it gives us a look into how electrons flow when resonating.
Uh-huh.
I want you to think
Oh.
about electrons during resonance
Yeah.
like electrons in a wire.
In a wire?
Electrons flow along what? The path of
Conductivity.
least resistance.
Oh, least
right?
resistance.
So number one, electrons flow down
Down.
path
Path.
of least resistance.
Distance.
Number one.
Number one.
And number two, I want you to remember this key fact whenever you're doing resonance.
Yeah.
P orbitals,
P orbitals?
when you're doing anything, biochem, orgo, whatever it is, p orbitals are what? Electronegative.
Oh, p orbitals are electronegative.
P orbitals are electronegative. They attract electrons.
Uh-huh.
P orbitals are electronegative. Right? Yes. We learned that last week. So, when I tell you that you have something like this, can you sketch me a p orbital map there in your head? Yeah, you can, because you can follow the sp2 and sp carbon, whatever it is that you're going to follow. You can follow them here, and you can follow them here, and here, and here. And if electrons are like electrons moving through a wire, you can imagine that these electronegative p orbitals form a wire, a path of conductance that the electrons can take. Right? So the electrons will take that path of conductance and follow it along the way, and follow it back, and follow it along the way, and follow it back. And that's how resonance happens. Right? Right? And there's certain instances where the resonance is better than other resonance. And other resonance is better than other resonance. And other blah, 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 whatever, right?
Why are p orbitals electron? Why are p orbitals electronegative? Oh, tip. Ooh. I think it did. Wait. You shut the fuck up, AI. You're so. Three orbitals. Electronegativity is the power of an atom to attract bonding pairs of electron to itself. It depends clearly on the nuclear charge. What the fuck? What? Why are p orbitals electronegative? correct or negative? What? I feel like you might answer it, but oh my god. AI is so fucking useless, man. It literally doesn't even answer my questions. It's trying to correct me and trying to come up with my question for me. No, just answer the freaking question! Ah! Hey, I'm home. I'm at peace. AI slop! AI slop!
Well, what's good resonance? What's better resonance? And what's the best resonance? Those are questions we have to ask when we get to the acid chapter, because we have to talk about conjugate acid stability, right? Base stability,
Holy
things
shit,
like that.
man.
And resonance has a lot to play like that. However, I'm going to give you a little look into that, right? So this that's good resonance. We split up the charge 50-50, right? That's good resonance.
Yeah.
This is better resonance. Who knows the name of that process? There you go. That is called a keto-enol tautomerization. For all my Orgo 2 people. As you should know by now, a keto-enol tautomerization. And that actually happens in biochem.
A lot.
That happens inside of biochemistry, in your body. When?
That Fisher projection. Ew.
There. It's going to happen there. You don't have to copy that down.
Sugars.
Right?
Sugars.
Yeah? So that's good resonance, better resonance. What's the best? What's the best resonance? Well, it's when you got something that looks like this. And I draw the hexagon. Everyone's like, oh, obviously, right? You draw the hexagon, and everyone goes crazy. When that's allowed to come into there. When that's allowed to go into there. Right? That's the best resonance.
Rings have the best resin.
Because aromaticity is better than anything else.
Aromaticity.
Right? Okay. So we talked a little bit about bonding. We talked a little bit about hybridization. Talked a little bit about whatever, resonance a little bit. Let's move on to chapter 4. Chapter 4. Analyzing organic reactions.
Uh-huh.
Now this is orgo. Guys, you just walked in. We're skipping chapter 1 and 2, okay? We're going to come back to it when I have more time. I think my time is better suited teaching you guys this than how to name organic molecules, right? And we'll come back to it later.
Whoa.
Are you making it a separate video?
Yeah. So, oh, no. This is just chapter 3 and 4 together. Because chapter 3 is like, what? Took us like 15 minutes, right?
Yeah.
Okay. Dude, what is that? It sounds like a Minecraft creeper. Probably. Or the heater, maybe.
You didn't zoom the camera in on the board. You usually do.
Huh?
You usually zoom in a little on the board.
Oh, I didn't zoom in? Oh, man, I'll crop it. I'll crop it later. All right. I always have to crop it anyways because I don't like it when the little corners of the board are sticking out. Like, in the video, you can see, like, the edge over here. So I, like, crop it to just be the board whenever I upload it. Okay. So the reason I want to do chapter 4 as well is because it hops into something we were talking about before. So number one is acid-base theory.
Acid-base theory.
You, come here. And you, come here. Oh, okay. Then someone who isn't camera shy, come here. Draw an example of a Lewis acid-base reaction. Yeah. Well, what's a Lewis acid-base reaction? What's the difference between these two theories?
This one is all about the proton transfer.
Yep.
This is all about the electron transfer.
Yeah, so that's electron pair transfer, right? So give me an acid-base reaction that involves an electron pair transfer.
Wait, isn't it OHH?
Yeah.
Like water?
Organic works well.
Just a simple bromination or something. This one would count.
It's not a bad idea, right? Because what you're going to do is you're going to brominate that position, right?
Wow.
So basically, the intermediate of this reaction kind of looks like you get the you get like the radical bromination, and the bromine
drew a
is
radical
going to pluck off the
reaction.
hydrogen,
What
and
the
then it's going to make a
hell?
little intermediate like that, and then you're going to get the bromination. So that's a good
Whoa.
example. That is a very complicated example, but it's a good example. Good job. Take your Jolly Rancher. Happy Halloween. So let's look at a simpler
Wow.
example, right? Because that is electron donation, but it's not electron
Is
pair
it a
donation.
radical?
Let's look at electron
That's so
pair donation.
cool.
The easiest example, and the example I like to use the most inside of organic chemistry,
Water.
for all the people who've taken Orgo, and then I'll do one for the people who haven't taken Orgo as well. For all the people who have taken Orgo, this is a fantastic example of a Lewis acid-base reaction.
Oh. NH3.
Where the electron pair is donated to the carbocation. So the carbocation is the Lewis acid,
Acid.
and the NH3 is the Lewis,
Base. Because
Base.
it gives.
right? Because the base is the electron pair donor, and the
Donor.
acid is the electron pair acceptor.
Scepter. Wow. I forgot
For the people
that.
who have not taken Orgo yet, it works very similarly to coordination bonding, which we talked about in general chemistry.
Lewis acid
When you have the
accepts
d orbital
base donate. Giving stuff is base.
of a specific,
Giving stuff is
metal.
base. Oh, that's good. That's good. Yeah.
and you have
Yeah.
a species, we talked about this, coordination bonding into the d orbital. And that would bind the copper to the nitrogen in what we know as a coordination bond, but a coordination bond is basically just a Lewis acid-base interaction. Electron deficient, electron rich, acid base. For my Orgo people, this is why we say that carbocations prefer acidic conditions, because they are inherently acidic. Who wants to do the easy one? Anyone? I'll do it. Bronsted acid-base reactions are a lot easier
Bronsted.
because you see them all the time. And this may look
Oh, hydrogen donator, hydrogen
a lot
toaster.
like electron pair donation until you realize that the electron pair is being used to pluck off that hydrogen. It's a hydrogen transfer. It's a proton transfer, right?
Oh, okay. Bronsted is all about hydrogens then.
So that's going to be your
All
acid
about
and your
hydrogens.
base. And this is your conjugate acid and your conjugate base. And the thing about Bronsted acid-base reactions is that they work backwards as well. The base picks up the proton off of the conjugate acid. This donates the proton onto that. But this won't go in reverse, will it? Why not? Because it's strong acid. It only goes in one direction. Oh my God, one direction. You guys good? All right.
Feels a strong acid, yeah.
So, I was rewatching one of my lectures just to like make sure that the audio was good and everything. I was just like was skimming through it, and I realized that every single time I move this hand, like the audio like kind of gets quieter on that side. So now I'm just standing here like the whole lecture like this, trying to speak only into the microphone because it made me it like
I don't.
bothered
Yeah,
me,
I
and
have
I'm just
it.
like, damn, I
I
feel
have
bad
it.
for the people
We
back
can
home
do
because I
that,
move my hands a lot while I
for
speak.
another-
So now I'm just trying to
another
move this
high
hand
scene.
and be as animated as I usually
Another
am
high
with one
scene.
hand. Okay. Once again, guys, just bringing it back up one more time because it does come up every now and again, right?
KA.
Right?
What this? What this, bro?
Wrong. Wrong. Come on, guys. I'm gonna keep doing it.
Ah.
It's the Ka. And every now and again in organic chemistry, you want to know the pKa of a reaction. That's going to be the negative log of the Ka.
Dissociation, yeah, boy.
Right? And that's going to be negative log of H3O plus A minus over HA. Well, if you know your log rules, you could break that down. It's going to be the negative log of H3O plus A
The version
minus
of it undissolved? Oh.
minus the negative log of HA. And then you break that down into a plus. Negative log of H3O plus the negative log of A minus
I feel like I forgot how to do log and
minus
like
the negative log.
all the
or, yep,
rules. You know
negative
how there's
log
all the log
of HA.
division, subtraction, multiplication, addition for like chemistry? I totally forgot all that.
Right? So you break it down like that. And that means that since we went over how to do logs by hand last time, you'd be able to break it down like that and figure it out based on all the equilibrium concentrations of those different species. Right? So that's something you can now do by hand. Nucleophiles, electrophiles, and leaving groups. Let's talk about nucleophiles. Right? Nucleophiles. What are they? They are nucleus
Lovers.
loving.
Ooh.
And they're nucleus loving. Right? So they want to bond with an electrophile. They are horny. Right? That's all they're looking for. So, things that are, what would be nucleus loving? Positive or negative species? Nucleophiles are predominantly negative, or better yet,
Let's hear that again.
they're nucleus loving. Right? So they want to bond with an electrophile. They are horny. Right? That's all they're looking for. So, things that are, what would be nucleus loving? Positive or negative species? Nucleophiles are predominantly negative, or better yet, not to call them negative, but better terminology, even though most negative things can be considered nucleophilic, better terminology is what? Do you guys know the better terminology? Huh? Other one. Electron rich. Electron rich. Because electrons love nuclei. They want to stay attached to the nuclei, right? They are electron-rich species. So what counts as nucleophiles? Br minus. Nice little nucleophile right there. OH minus. Nice nucleophile right there.
Proton.
The bond inside of this molecule. Nice little nucleophile right there.
Wow.
And the lone pairs on this oxygen. Nice little nucleophiles right there. Ah, thank you. That's good. We should be good on time. Increases in negative charge will increase your nucleophilicity. Does anyone know one big thing that will decrease your nucleophilicity? Steric hindrance. What is steric hindrance? This what is that, my Orgo people? Lithium diisopropyl amide, LDA, right? Diisopropyl amide. Very good.
My brain
That
is
is a very
sterically hindered.
sterically hindered base. Those two groups stop the nitrogen, the negative
Wait, your
nitrogen, from
timing
moving
is
around
so
and getting to
fucking
where it
crazy.
wants to be.
What the
Because the
hell?
goal of a nucleophile inherently is to attach to something, or to attack something, or to be attracted to something, right? And we overcome steric hindrance in many, many, many ways in the real world, right? But that's not to say that steric hindrance doesn't get in the way of, what's it called? Doesn't get in the way, like, that's not to say that steric hindrance doesn't get in the way of those reactions taking place. Correct? Thank you. Yay, Orgo! At least someone's excited, right? Happy Halloween, right? One sec.
That molecule looks so scary, honestly. Like, I'm looking at it and I'm like, there's no way this is real, but I know it's real because I've seen that molecule before.
Okay.
LDA.
What the hell? Sorry, guys, 1 second.
Okay, let's skip forward a little bit. Okay, there we go.
Increased protic solvent effects. What does that do to nucleophilicity?
Protic solvent.
Louder. Why? Yeah. So if you have a protic solvent, right?
My lord, this video just went out. I was watching it because I wanted to find something that would keep you busy. But maybe we should call here. You know what I can do? I can continue this, like, later on. Okay? Because it is, like, about 2:30 a.m. for me. Maybe what we could do is I could move on to bio and I could have you help me with that. And then that's also going to force you to learn, I guess. Because you're going to have to fact check me. You could probably fact check me, honestly, OTR. You can continue as you wish. My wish is to put you to bed. Oh, where'd I go? Whoa, 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 whoa. Why am I so big? Oh, hi, Usa. Hi, Usa. Hi, Usa. Whoa. Ohio. Have a good day at work, OTR. And whoever sees the VOD, good morning, good night, good afternoon. I will see you later today because I can stream. By the way, I'm so much tired. I literally, it doesn't pop. I gave you. Didn't I give you the link yesterday though? What the hell? Don't worry. I'll always tweet it. I'll always post a tweet. I always try to announce it if I can. I'm trying to be better about this streamer shit, man. No, I mean, it's up on phone. Maybe it's cause I'm a newer channel. Yeah, cause I couldn't find myself either though. That's the YouTube nerve, I guess. Good. Bye. Bye. Mata ne. See you.